All right, so where we were yesterday is we just used, or whatever, several days ago, we just used the power and the voltage on the second circuit to calculate the current, that was pretty straightforward, P equals IV. And then the second, the second part is we're supposed to say if the first circuit has 60 ohms of resistance, then what is the current there? Well, we're given the voltage for the first circuit, so we can just come up with 2 amps. Now we're supposed to come up with the current for the second circuit. What do we know? We know the second circuit has the same isn't that the same voltage? Oh, okay, yeah, there's no voltage there. Okay, so now we can just use, yeah, we don't know the voltage of the second one. You probably have to use the turns to get the voltage. Let me look at the book. Bulb. So they're telling us that there's no resistance on the second circuit. If we have this current on the first circuit, then this voltage isn't without anything happening on the first circuit, over here, nothing happens over here. There's no battery over here. What this 120 volts means is that this bulb operates on 120 volts. So if you put less than that, it may light dimly or not at all. And if you put more than 120 volts, obviously what's the bulb going to do? Yeah, it's going to burn out. So the idea is we'll probably have to use a couple of equations. So the first one is, I would say, let's see if we have a 2 amp current running through this first circuit at 120 volts. Let's figure out what the voltage is in the second circuit and then find out what happens to the bulb first. So if we do EMF1 over EMF2 equals N1 over N2, then EMF2 is going to equal EMF1 times N2 over N1. I think. Yeah. Okay, so that means EMF1 is 120 volts, N2 is 1,000 over 100 for N1, and basically we get 1,200 volts. So the 1,200 volt, that's going to blow out the bulb. Interesting. And then, after we do that, I'll do this in a different color so we can see, right? So this was one of the equations, right? And what was the other equation for transformers? Yeah, I1 V1, equals I2 V2, or P1 equals P2. So if we go I1 V1 equals I2 V2, okay, then we can say I2 is going to be equal, is this recording? Yeah. I2 is going to be equal to I1 times V1 over V2. All right, so V1 is 120, V2 is 1,200, so it's 1/10. So then this current is going to be 0.2 amps. So it's going to have a small current, but it's going to have a huge voltage. And what's going to happen to the bulb? Burnout. Okay. Then the last part, part D, it says if the resistance in the secondary coil is negligible, what must be the resistance of the primary coil for the bulb to glow at its customary brightness? So we just saw that if the primary bulb or primary circuit is 60 ohms, then this bulb's going to burn out, right? So the question is, what does the primary bulb's resistance need to be in order for the secondary, the bulb, what does this resistor need to be? What does R1 need to be in order to keep the bulb from burning out? So what that tells us, right, is that we need E2 to be 120 volts. Does that make sense? Because 120 volts is what the bulb's rated at. So we have to figure out a way to get E2 to be 120 instead of 1200. Now, if we just stop for a second and go back through this logically, right, then we see we can't change the effect of the coils, right? They're saying just change the resistance. So we have to do something that will allow us to change E1. Does that make sense to you? Okay, because N2 over N1 was times 10. So we need E1 to be 10 times less, right? So if we do that, and we go back over to here, E1, which is V1, is 120 volts. So if, I know, that's not gonna work. That's not gonna work. The current isn't what will burn it out, it's the voltage. That's interesting. Oh, you did? Oh, okay. All right. Let's not worry about voltage and say the thing that's going to burn out. Like what causes the bulb to be brighter or less bright? Yeah. How do you rate in a circuit with a bunch of bulbs? How do you rate which one's the brightest? What is the physical quality that says, oh, that one's brighter? Yeah, watts. It's power. Okay, if you look at the power that is output by the different bulbs, then you would say, okay, now in reality, that's not the case, right? Because you can have like a 23 watt fluorescent bulb that produces the same amount of light as a 100 watt or 60 watt incandescent bulb. And then you can have like an 8 watt LED bulb that produces as much light as that 60 watt incandescent bulb. When I say incandescent, do you know what I'm talking about? Yeah, incandescent means like the little wire inside, the little loopy wire, it's like hot, right? And then fluorescent is like those squirrely noodle tube bulbs, you know, where they go, whatever, I don't know. Or like these are fluorescent, these long white bars. And then LEDs, of course, everybody knows what that is, right? My solar flashlight, isn't that useful? Is that bright? No, you can't. I'm just kidding. It uses a solar cell to charge the battery. But actually, I don't even, yeah. Anyways, so in real life, as a point of life, remember that bulbs on the shelf at the store are usually rated in some. Anybody know? How do they rate the bulbs for brightness? Yeah, there you go. They're usually rated in lumens. So when you want to buy a bulb, don't just buy a bulb because of the watts. Buy the bulb because of the lumens. All right, and I think, yeah, by the time your age, I think they'll have paint, but that just, you paint on the ceiling, it just lights up. Yeah. I think they will. Because they can already do that, but the problem is it's very susceptible to water. So humidity causes the molecules to degrade. Anybody in here have an Android phone? Like an HTC Android phone or a Samsung? If you have a Samsung, then you have an organic light emitting display, LED, an OLED screen. If you have a Samsung, I think almost for sure you have an OLED. If you have like a Nexus 1 or a Nexus S or a Galaxy S phone, most of those have OLED displays. And those displays are actually they're lit up. Is this recording? Oh my gosh. Second record again after all that crap. So power is what we need to focus on. Where does the power come from? It comes from the voltage and the current. Okay? Does the resistance of the first circuit, does that affect the voltage of the first circuit? If I take a resistor and I put it in a circuit with a battery, can I make that resistor make the battery increase or decrease its voltage? No, you can't change the battery. We are given 120 volts. And they're telling us that we need to change the resistor. So what is the only thing we can change about the first circuit? If we change the resistor, what is the thing that's going to change? Yeah, not voltage, but current. So when we look at what the first current did, the first current set up the second current, right? That's how we got the 0.2 amps here. And the voltage here in the second current is a function of the first voltage and the coils. Can we change the first voltage? No, we already said we can't. Can we change the number of coils? No, because they said all we're supposed to change is resistance. So we can't affect this voltage. This circuit has to stay 1200 volts. But what can we change? The current in that second circuit. And then now, do you see, because if we look here, where do we get the current in the second circuit? It's a function of the current from the first circuit. And where did the first circuit's current come from? It came from that resistor, right? So all we have to do is ask ourselves, and I'm going to need to probably stick a new, I need to stick a new page in here to do this. So V1 is constant. I1 is a function of R1, which is what we're trying to change. V2, because it depends, V2 depends on V1, N1, and N2, and none of those can change. So V2 is 1200 volts. We can't affect that. But I2 is dependent upon I1, right? And because I1 is dependent upon R1, we can change that. So how do all these things play together? All right, well, the power for 2 is equal to I2 times V2. Okay, we already know that's 1200. So we need this value to be equal to 60 watts. So then we need current 2 to equal V2 over 60 watts. No, that's not right. 60 watts over V2. That's better. Does that make sense? Now, where did current 2 come from? That came from this. So I2 over here, is that recording? Yes. I2 is equal to I1 times V1 over V2. So we can stick this in, and where did I1 come from? I1 is equal to V1 over R1. So we can take this, stick that in there, and then take that and put it over here. So then we're going to get V1 squared over V2 and R1 equals this stuff. So ultimately, if we, and then these two are equal to each other. So if we solve this for R1, we get R1 is equal, oh wow, look, the V2's cancel. Whoa, that's crazy. Well, whatever, it is what it is. Let's see if it works. So R1 is equal to V1 squared over 60. And V1 was 120. So 120 squared is 1440? No, 14,000 or something. 14,400? Is that right? Yeah, 120 is 1.2 times 10 to the 2, so squared, that'd be 1.44 times 10 to the 4. Yeah. Divided by 60. Okay, that's really tiny. What does that come out to be? I wonder if that works. That goes away. 240 ohms. Is that what it comes out to be? Yeah, that makes sense. 240. Now, remember, through our logic, before we went off on random weird topics, through our logic, we said that this power, the 0.2 amps and 1200 volts, the power of the second circuit, right, it came out to be like 240 watts, which is what burned out the bulb. So how much do we need to decrease that power? By a factor of what? Yeah, by a factor of 4. Does that make sense? So we need to make that 4 times less powerful. So what we thought was, if we could we can't change the voltage, so we need to take the current and make it 4 times smaller. Which means the original current had to be 4 times smaller. And how do you make current smaller? What do you increase? Yeah, if we make this resistance 4 times bigger, ding, 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 we'll get what we want.
Maybe the book says 24 ohms.
24 ohms?
Yeah.
Interesting.
Yeah, maybe it's faulty. Maybe it's not.
Okay, so yeah, there you go. That was a fun one. So yeah, I guess finally, to sort of make sure we know where we're at, certain things couldn't change. The 120 volts in circuit 1 is given. The number of coils makes that voltage ramp up to 1200 volts. So that's unchangeable. We can't affect that. So how do we get the total power to be 60 watts if you have 1200 volts? Right, well, you have to have a very small current. So we can find out, you could actually do that now if you wanted and find out what that current is. And then you could say, since that current, right, this one, the really tiny one that we need, comes from the ratio of the voltages, then we could plug that in and find out the current that we need in circuit 1. And then once we found out that circuit, then we can use Ohm's law to find the resistance, instead of trying to put it all in one if you wanted to do that. Okay, well, there you go. That's that.